4 event selection card. The first is the trigger selection, then physics selection, and then I will go to the Pileup rejection, then vertex selection and centrality estimation. And for the more details about this event selection, one can look at this Alice Wiki page of this event selection. So let's start with the trigger. So in Alice experiment, we cannot record all the events because of the large detector readout time, which is up to 1 millisecond per event, and the data storage limitation. That is why we selected events for our analysis using some triggers. Now, in general, the widely used trigger that we used mostly in our analysis is the minimum bias trigger, which is mainly based on the information from V0, SPD, and T0 detector. There are also several other triggers for rare physics like muon trigger, calorimeter trigger, and this. But in this lecture, I will mainly focus on this minimum bias trigger. So this minimum bias triggers, there we can have two type of different minimum bias triggers. One is KMB, another is KN7. So this KMB, we generally used it in round one data. For example, lead 2.76 data. When we analyze the lead 2.76 TV data, we generally use this KMB trigger. And in run two data, we used a more stricter condition, that is the KN7 trigger. So what is the condition for KMB trigger? That you need hit in any of these three detector, SPD, V0A, and V0C. And for KN7, the condition is that you need hit in the both V0A and V0C. Now, how can we implement this trigger condition in our analysis? We can do it by calling the Ali V event class. So you can basically call in this Ali V event class. You can, if you open this class in your AliPhysics or AliRoot, you can see there are several trigger options that is listed. And among them, there are two are the KMB and KN7, which we generally used in our analysis. And to get the more information about the different kind of trigger and their definition, you can always look at the header file of this Ali event class. Now, as I mentioned that this trigger that we are used, that is the KN7 and KMB, that's basically some combination of V0A and V0C and SPD V0 and V0C. So it's not only that, it also have several other things. For example, these triggers that are basically a combination of several trigger class. So when an event is occurred, it fired several trigger classes. And what is this trigger classes? This trigger classes is basically store the information about the event. So for example, here I write a trigger class. You can see that is scene 7B, no PF, then sent no TRD. So what does this mean? So this first thing, that is the scene 7, that is basically the descriptor. That basically tells us about the logic that we have used for the trigger. For example, AND logic or OR logic. So here we basically have the information that we used is V0A and V0C, or V0A or V0C, etc. Then this B stands for the BC mask. So that is basically gives us the information about the collision. If the collision is a proper event, that is the beam collision, or it is a background, that is if it is a beam gas event, etc. Now we have another thing, that is the no PF, that is basically store the information of Pileup, that is basically store the information of past and future Pileup, which reject using this information one can reject the Pileup event. And in the last, this is basically store the information of the cluster. So one can look at here in below. Here I wrote here I show the several type of cluster. And if you look at this sent no TRD, so the sent no TRD is basically is the combination of cluster from EMCAL, SPD, TOF, TPC, and V0. So for example, there are several other kind of cluster like all no TRD, all sent, etc. Now, for example, what is our this Kane sent trigger is made of? So the Kane 7 trigger is made of with these several kind of trigger. So in Kane 7, with the Kane 7 trigger, we basically select events which at least one of these following trigger class that fired. And usually this Kane 7 trigger class is active in a means in a given run. For example, in a given run, you always have the same trigger. So that is the basic idea about this Kane 7 trigger. Now let's go to the after means with the trigger we basically select a fraction of events from the total events for our analysis, but those event is consist of various background and pile up event or etc. So we need to remove those background and pile up events. So for that we generally started with the physics selection. So what is this physics selection? So this physics selection class is used to select events with the trigger class that I have already mentioned. In addition to that, it also allows us to reject background and poor quality events that are coming from the, uh, say example, a collision of a beam in with the residual gas in the vacuum beam pipe. And it also allows us to reject the out of branch pile up event in the SPD readout time. I will come to this. What is this out of branch pile up in the SPD readout time? When I will talk about the pile up rejection cut. Now, how to include this physics selection cut in our analysis? So it can be done in a two-step. So in first step, you need to add this task. So this is basically additional task. In addition to or your own analysis task, this is an additional task which first select some event, then it propagate to your task. So you can directly do it by putting this line in your steering macro, that is runAnalysis.C. So what you need to do, you just need to load the macro of physics selection, that is the add task physics selection. Then you need to call the task of the physics selection and put some argument. So here is two argument. One is the MC flag, another is the apply pile up card. So these two arguments is basically a Boolean type. It is either true or false. So in case of data, we use this MC flag false, and in case of Monte Carlo, use this MC flag true. And this apply pile up cuts, we use this always true to reject this out of branch pile up event in the SPD readout time. Now, how to, you can also select the trigger information from this physics selection. In order to do that, you can do it in a two-way. In your AddTask macro, you can directly call the set collision candidate and then put the trigger information, this Kane 7. And as I mentioned you that this trigger information is obtained from this LEV event cut, LEV event class. So you just need to put LEV event, then Kane 7. And you can also include this trigger information in your analysis task in your user execute of your .cxx macro by putting these two lines. So here in the first line, it will basically call the event from the event input event handler. Then it checks if there is an event handler, and also the event is from the Kane 7 trigger. So by putting these two steps in your analysis macro, you can directly implement the physics selection, which will basically reject this background and the out of bunch pile up from the SPD readout. Now let's go to into the more details of this physics selection. So as I mentioned that this uh, physics selection reject your beam induced background, that is the collision between the your beam and the residual gas in the beam pipe. So how one can do it? One can do it using the information of V0, SPD, and JDC. So here I showed two particular example. For example, you can directly reject this beam-induced background by doing a correlation between the V0C time and V0A time. So what is this V0A time? So this V0A time is basically the time of flight of particle from the interaction point to the V0A detector, and similar for the V0C. And if you look at the correlation plot, you can see that here is a bunch of events. So these events are basically our beam event or original PP collision event. It occurs, you can see it occurs, it means around at V0 around 11 nanosecond, and V0C around 3 nanoseconds. So why this different? This different is because the V0A is placed in the display, the distance between the V0A and the interaction point is more compared to the V0C. That is why you can see that for the V0C, the peak is around 3 nanoseconds, but for V0A, the peak is around 11 nanoseconds. And in this correlation plot, you can see there are other several branches. These are basically the your 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 beam gas event. So these are basically the background in your analysis, which is coming from the collision of a, for example, proton and gas. Now you can also reject this background. In addition to that, you can also implement another. We have also implemented additional cut in this physics selection by looking at the correlation between the tracklets of SPD and the cluster of SPD. So this is the correlation plot of the tracklet of SPD and cluster of SPD. And you can see that except this proper correlation, one-to-one correlation, there is other data points which are basically your background. That is basically your beam gas background. So you can directly reject this by putting a linear cut, which is already implemented in the physics selection. So by the applying the physics selection in first step, you reject these backgrounds, this beam induced background. Now, in case of run 2, where in case of run 2, we have also added further more selection cut to reject this background. So those selection cut is basically
Excuse me, sir.
yeah.
Sir, in the previous slide, yeah,
Yes.
if I couldn't understand this x-axis and y-axis. This
So this here
n
or
tracklets
here.
and n clusters.
So this
Yeah,
n
yeah, yeah.
tracklet,
Right side,
so
yes.
this yeah, so this n tracklet is basically the number of tracks. So what is the tracklet? So the tracklet is basically made from the two heat of the SPD. So SPD, you have the two layers, and
Okay,
using the two heat, you made the SPD. So it's basically the number of tracklets, and the SPD and the n cluster is basically the SPD cluster. So what
okay,
is this SPD cluster? So this SPD cluster is basically the number of what is it? That is basically the number of chips in the SPD that fires during the collision. So
okay.
these two
So,
should be always linearly correlated because this number of cluster that fires, it should be proportional to the number of tracklets. But here you can see that there are some event in there low tracklet, but you have a large number of fires. So that's basically coming from the background. That means you get hit in the SPD, but means you get more cluster in the SPD compared to the tracklet. Those are basically the background.
okay, thank you, sir.
Okay. Okay. Now here I'll show the so as I mentioned that in run to analysis, we have implemented further more rejection to reduce this background. So that's basically by using the correlation between the V0 different layer of V0C. Yes, so in the V0C, we have basically four rings, 0, 1, 2, and 3. So this first plot is basically the correlation between the multiplicity obtained by from the hit in the first three rings, 0, 1, 2, and with the correlation in the third ring. And in the next correlation is the correlation with the multiplicity obtained from the first three rings 0, 1, 2 of the V0 with the number of tracklets. And you can see that one can put some cuts here to reject this background which is outlier from this correlation. Now, after removing this background, we applied this Pileup cuts that I have mentioned previously by just putting this apply Pileup cuts true when you call this AddMyTask.C in your macro. So it will basically reject the out of bunch Pileup using the V0 future past information and some correlation between the V0 online and offline and SPD online and offline multiplicities or clusters. So let's in this Pileup section, I will talk about it. So let's now go to the Pileup. So In our experiment, we basically have two type of pileup. One is the same branch crossing pileup, another is the out of branch pileup. So what is the same branch crossing pileup? So the same branch crossing pileup is basically the two or more collision occurring in the same branch crossing. Means when we have the beam, so this beam is coming in a bunch, and when you have the collision in the same bunch, that is more than one collision, that is called basically the pile up in the same branch crossing. And when you have the collision in the different bunch, then we just called it is the out of bunch pile up. So how this affect our detector? So this same bunch crossing pile up will be means it will be seen by all the detectors. Basically, when you trigger some event, you trigger over a bunch, and if in that bunch, if you have multiple collision, then you will able your all the detectors will be able to see those collisions. So all your detector will be affected by the same branch crossing pileup. Whereas this out of branch crossing the pileup will affect the detector depending on their readout time. What that means? That means, for example, the SPD, it has a readout time of around 300 nanosecond. So in a collision, when you trigger the event where it has a hit on the SPD, so in that case, it will see events in that branch, and also additional to that branch, it can see the events in neighboring other 12 branches. Why these 12 branches? Because you know that the time spacing between the two branches is around 25 nanosecond, and if the readout time of the SPD is 300, then in order means when SPD complete the readout of one event at that moment, it there is a possibility that there it can take heat from the other neighboring 12 branches. So if you just divide this 300 by 25, you can get this 12 branch crossing number for the SPD. But if you go to the more slow detector, for example, like TPC, where this readout time is, I think, around 100 microsecond, there you will get the information of around 4,000 branch crossing. So it will basically see the effect of pileup from the neighboring 4,000 branches. So therefore, this out of bunch pileup is affect the detector depending on their readout time. And using this information, this different readout time of the detector, one can reject this out of bunch pileup. I will show you it later how to do it. I mean how we do it. Then the same bunch pileup, it will not. You can see here that the same bunch pileup, uh, it will not affect this reconstructed point in the deep detector like TPC and HDD. But in case of out of bunch pileup, it will affect the reconstructed point. And this same bunch pileup, how can we remove it? One can remove this same bunch pileup by removing the event, by looking at if in your recorded event is there is multiple reconstructed vertices. So if you record, if means in the event, you can reconstruct your vertices, and if you see that if your tracks is matched to several vertices, then out of those vertices, one will be your primary vertices, and other will other will be probably the pile up vertices. So by looking at the multiple vertices in the event, you can remove this same bunch crossing pile up. And how one can remove this out of bunch pileup? One can remove it by doing the event selection, as well as one can reduce the effect of out of bunch pileup by rejecting the tracks that are coming from this out of bunch pileup. I will talk to I will talk it later. Talk about this. Then let's first start with this pileup in the SPD. So this basically called the uh, past future protection, or the past future pileup. As I mentioned you that the SPD readout time is around 300 nanosecond. So here in this plot, you can understand it. If you trigger a event, for this boxes are basically the bunches, and if you trigger a event which is in this branch, so SPD will see the information from this collision as well as from the other collision if it is happens in the nearing these 12 branches. So if there is any event that occurs within this SPD readout time, that will give you a Pileup, and this Pileup you can reject it using this Alice physics using this AliPhysicsSelection, where we reject this Pileup by using the information of the V0 detector and some correlation with the V0 and the SPD. So you need to remember, when you do your analysis, you need to put this second argument in this at task physics selection k true in order to remove this out of bunch pileup in the SPD integration region. Now let me go to the another type of pileup. In the previous slide here, I mentioned about the out of bunch pileup. Now let's see how we can remove the same bunch pileup as well as the out of bunch pileup in the SPD readout window. So as I mentioned that the SPD has a very good uh, means it is a very fast detector. So you can by taking on, if you consider that your events has a hit in the SPD, in that way you can neglect a huge amount of out of bunch pileup, but you cannot remove all the out of bunch pileup. You need to remove this out of bunch pileup that is happens in the SPD readout window. We did it with the AliPhysicsSelection task, but using the AliPhysicsSelection, we cannot remove it completely. That is why we need to put another selection, that is the we need to search if there is any multiple vertices in that event. And how can we do that? One can do that using by calling this is pileup from SPD from this AliESD event card. So if you call this is pileup from SPD in AliESD event card, it will give you that if there is more than one vertices in that event, it will give you that it is coming, that event is basically affected from the pileups. Okay, and now how we define which vertices is the primary vertices and which is the vertices is coming from the pileup. So for that, we check the number of cluster, or the number of contribution, number of contributor. So you, when you reconstruct the vertex, you basically see that how many contributors you means how many contributors is associated with the vertex. So this contributor, you can think it about like a multiplicity or number of tracks. So we assigned the vertex as the primary vertex which have the largest number of contributors, and the vertexes which have less number of contributor, we assigned it as the pileup vertices. Now in this function, you have several argument. You can see it. I have put some number here. So what is this argument means? This argument give you some freedom to control this selection on the vertices, or the selection on this same bunch pileup or the out of bunch pileup in the SPD readout. And these arguments are basically, here I have quoted this argument. These are, the first argument is the minimum number of contributors of the pileup candidate vertices. So if you have a, you first check if you have how many vertices you have, then you assign the largest number of the vertices, the vertex with the largest number of contributor you assigned as a primary, and the others are the pileup vertices. Then you check the minimum number of contributor in the pileup vertices. So the three means if there is the minimum number of uh, vertices with the minimum number of contributors corresponding those vertices is 3, then you just assigned it as a pileup vertex. Says then you have also the condition on the minimum distance along the z direction between the main and the pileup vertices. Means you have one main vertex and other pileup vertices. You can check the direction or the z direction in the z axis between those vertices, and you can put a minimum cut. Then you can also check the minimum distance along the z direction between the main and between the main vertices and the pileup vertices in terms of n sigma. So you calculate the distance, then you divide it with your vertex reconstruction resolution to get the number of sigma. Then you have you also have a handle on the cut on the maximum distance from the center of diamond in the transverse plane in terms of number of n sigma. So what is this diamond? So in a given run, you will have you will have many events. For that many events, you will have many vertex. So you just calculate the mean of the vertex, and that mean position is basically your interaction diamond. And you see the distance of those vertices from the interaction diamonds in terms of sigma, where is the sigma is your vertex resolution. And you can also do the similar thing in the longitudinal direction. So you can control this condition in your analysis to reject the pileup events from the SPD. Now here I quoted two examples for this condition is basically used for low multiplicity PP event for, and this condition is basically used for the high multiplicity PP events. And you can see the differences between the number of contributors associated with the pileup vertices. In low multiplicity is 3 and high multiplicity is 5. Because if you go to the high multiplicity, you will expect more tracks, so your vertices will associate it with more number of contributors. You can directly do it using a multiplicity dependence pileup rejection cut of the SPD by calling is pileup from SPD in multbeans. So in this function, the multiplicity dependence is implemented in such a way that if your number of contributors is less than 20, means the number of contributors is less than 20, then it will take the minimum number of cluster 3. If it is between 20 to 50, it will take 4, and if it is greater than 50, it will take 5. So in your analysis macro, when you get the pointer for the ESD event or AOD event, you can directly call this function is pileup from SPD mult or is pileup from SPD to reject this same bunch pileup and out of bunch pileup depending upon your condition what you have put. Now, one can also this reject this multiple vertices which are reconstructed from the track. So in the previous example, this multiple vertices are reconstructed by the information of from the information of the SPD. And here you can also do it by taking by reconstructing the vertex by taking the track information from ITS, TPC, and TOF. You can find the multiple vertexes and you can reject it. And you can do it by using the use pileup multiple vertex. So you just need to in your analysis task, you just need to call this AliAnalysis utilities class. You can call it using a pointer, and then you can just call this function and put your event that you have put your event that you have selected in your user execute in this argument. Then it will give you a true or false value, that is basically the boolean value. And if it is from pileup, then it will give you basically a true. Then in case of lead-lead collision or heavy ion collision, we also used some additional pileup cut to remove the pileup event. And this additional cut is done using the correlation between the V0 and SPD. So here you can see there is a correlation between the V0 and CL1 in the centrality percentile before cut and after cut. So you can see in the before cut, you have some outlier. You have some outlier from this main correlation. Then if you can put some cut here, you can reject this outlier, which are basically the pileup events. So what is this CL1? What is the CL0 and CL1? So the CL0 is basically the it will basically do the multiplicity estimation by using the cluster from the first layer of your SPD information. And the CL1 will do it by using the taking the information of the second layer of your SPD. Means you just check that if that track has a hit on the first layer of the SPD and the second layer of the SPD, then it will calculate the centrality percentile, and it is basically the correlation between that CL0 percentile and this V0M percentile. Now, till now I have told you how to reject this pileup event. So in using this cut, you can directly reject the events. But there is also possibility that you do not reject the event, you just reject the tracks that is coming from the pileup event. And why you need to do so? So in many of the run to sample, a large fraction of data is recorded where you have more than one collision in the TPC readout. So if you have more than one collision in the TPC readout, that means you have more than one vertices for most of the event recorded. And if you're going to remove the events by looking at the multiple vertices, then it will significantly reduce your event statistics. In order to avoid that, one can put some cut on the track level to reject the track that is coming from the Pileup event. And how can we do that? We can do it by two way. So the first condition is that you need to put a condition that you only will take those events in your analysis which have at least one hit in the SPD layer. So in that way, SPD is a fast detector. So in that way, you can remove the tracks that is are coming from the out of bunch that is are coming from the other Pileup events. And in order to do that, how can you do that? You can do it directly when if you are doing some analysis with some ESD data. You can directly put this condition in your ESD track cut by allowing the allowing the condition that you will use those track which have the status of ITS refit. Means you will use that track which is means when you reconstruct the track, you just feed the hits. So during the fit is you need to also include the information of the ITS. So this if you use this KITS refit, means if you use the track which is reconstructed using the information of ITS, you can remove this Pileup. In addition to that, you also need to put this condition of the SPD that your track needs to at least one hit in the SPD. And you can do it by putting the set cluster requirement ITS. And here you can put the argument is the detector name, which detector you want to include. So I have mentioned that we need to include the SPD. That is why you put SPD. And here you, in the second argument, you put the condition, how many cluster requirement you want from the SPD. So in generally we put just any one, means at least one cluster from the SPD. In this way, one can reject the tracks coming from the Pileup event. Now you can also do it in the AOD level. If you are doing an analysis with the AOD level, then you can do it by just calling the if you have the AOD track, then you can just call that if the AOD track has any point in the ITS layer, and if it is means you can see, you can put it condition like hit in the any one of the ITS, any of the ITS layer, you can put the condition here, just looking at the by just calling the hash point on ITS layer. Now in addition to that, there are other additional requirement in the track level that you can use to remove these Pileup tracks. That is basically by using the information of top. So if you look at the means if you check if the track has any hit in the top or not, then in the most of cases your track which is coming from the Pileup that will not have any hit in the top. So if you do some top matching of your track, in that way you can reject the tracks that is coming from the Pileup events. And you can do that by just calling that get top branch crossing and check if the status is equal to 0. So if the status is equal to 0, that means your track has a hit in the top, and that means it is probably not coming from the Pileup events. So till now, I have mentioned about the Pileup events, what are the type of the Pileup event and how can we reject it. We can reject it by rejecting the event, and we can also reject it by rejecting the track that is coming from Pileup event. In addition to that, we also select event. In addition to that, uh, we also select event with some proper vertex condition. So we have events, the event vertex, if you look at the event vertex in the Z direction, it's basically have a Gaussian shape. In most of the cases, mean at 0, and then it's gradually falls down if you goes away from your interaction point. Now in this reconstructed vertexes, one need to put some cut. So first cut is to get a proper reconstructed vertexes. So how can we do that? How can we select a proper reconstructed vertex? So first you can select the vertex information from this AliV vertex. So you need to call this class AliV vertex. Then you just need to check the event. So if you have the LHD event, then you need ESD event, then you need to put the event pointer here for the ESD event in your user execution function. And if you have the AOD, then you can put the AOD. Then you need to get the get primary vertex. In that way, you will get the information of the primary vertex. And if you then put this if you can now if you then want to select what is the vertex j, then you can just call this vertex j and call the get and can call the get vertex j to get the z information of the vertex. Now how this class works means you can reconstruct this vertex using the track from SPD, using the global tracks, or using the track from TPC. So if you call this class if you call this get primary vertex, what will it return? So it will return you the vertex information in some particular way. So the first preference is that it will reconstruct the vertex using the global track. That means the track which is reconstructed using ITS, TPC, and TOF. If there is any hit in the TOF, then it will basically give you using those tracks, it will reconstruct the vertex and it will give you the XYZ information of the vertex, where the vertex is reconstructed from the track of the global track. So if there is if it is failed to reconstruct the vertex using the global track, it will goes to the vertex which is reconstructed from the SPD vertex. And if it is fails, then it will go to the vertex which is reconstructed from the TPC tracks. So it will give you the vertex information in this particular sequence. So the most it will always means in this particular sequence. Now after getting this vertex information from this LEV vertex, you also need to put some additional cut on the selected vertex to ensure that you have selected a good vertex. So the first cut is that you always need to put a condition that your vertex have more than one number of contributors. So why so? So if you have a less than one number of contributor, that basically means your vertex reconstruction is failed. And when your vertex reconstruction is failed, the reconstruction algorithm just put a value of x equal to 0, y equal to 0, and z equal to 0 of your vertex. So if you do not put this condition, you can see in your vertex jet distribution, you will get a sharp spike at v equal to 0, which is basically the due to the vertexes which are not properly reconstructed. In order to remove that, you need to put this condition vertex get and contributors greater than 1. Now you can also put additional condition on this vertex using some SPD. So you can put the using if you look means you can see if the vertex is uh, reconstructed in 3D using the SPD tracklet, or it is reconstructed in the Z using the SPD tracklet, and all those things. And you can also put there are other some additional criteria. So I will not go through that. I will just briefly say what are those, and the implementation you can find here. You can just put it is in your user execution of your analysis task to implement those selection. So the another additional vertex selection criteria is basically it is in order to is basically using the resolution and the dispersion of the vertex z position. And the another is using the absolute distance between the track vertex, absolute distance between the by using the absolute distance between the vertex reconstructed from the track, that means the global track, and the reconstructed by using the SPD tracklets. You can put a condition on the difference between the vertex jet using the SPD and the global track by some amount 0.5 in order to uh, reduce the events where you have do not have the proper vertex. Then you can also do it by putting some absolute n sigma, means in the previous here you have calculated the distance between the primary vertex reconstructed from global track and SPD track, and you just need to divide this distance with the vertex reconstructed resolution to get this in terms of sigma. So the implementation is here. Look at you can look at it to get how one can implement it in our code. Now, till now, I have mentioned several type of event selection card like Pileup event cards, cards on the proper reconstructed vertex and all those things. Now, how one can implement it in a very simple way. So there is a way, there is a class that called the Ali event class, and by calling it, you can simply implement all the above mentioned card, all the cards that I have mentioned above in you by using this L event card. So what you need to do, you just need to create a object of this L event card in your header file of your task by putting this L event cards and say some name AF event cards, which are basically the public variable. Then you can just check by that the if the event is accepted or not. You can do it by just putting a dot. By dot means you just call the function or the member from this ali event cards, and you call the function accepted event, and in the argument you just put the pointer of your event. If you have ESD event, then you just put the pointer of the ESD event. If you have AOD event, you just put the pointer of the AOD event, and it will tell you if your event is selected or not. Means if your event is selected after implementing all these cards that I have mentioned above. So the advantage is here that this task is written, this class is written in such a way, it uh, it has some particular default selection depending upon your data set. Means are you using the PP data set or data set from which year. Depending upon that, you have some default selection card which is uh, defined by in the data processing group, and you have those cards implemented here. So you just need to call if the event is accepted. And in addition to that, using this class, you can also show some QA plot. So you just need to add this add QA plot in your output list in your user create output object, where you define or where you initialize your list and histogram and all this output file. There you just need to add this QA histogram in your list by using this command. So this command will basically give you those correlation plot that I have showed, the correlation between V0 SPD, distribution of vertex Z before and applying cut and all those things. Those QA plots you will get by just applying this line in your user create output object. Now, so these are basically the standard thing. So I would always suggest to use those standard event selection card first for your analysis. Then if your analysis demands any additional selection card or any additional modification on the Pileup, some tighter Pileup cut and all those things, then you can do it manually you can do it manually directly from these LE event cards. So in the next slide, I will go how to do it manually. How can you apply some advanced selection card over this default card. So you can you can directly do it. You can see here I have put it some lines to do some advanced setting. For example, in default, your vertex date card, if you call this f event cards dot f minimum vertex date, it will give you basically the minimum vertex date card. In default, by default, it is -10. If you want, you can change it from -10 to 5 or -10 to 7, depending upon your analysis. So in order to apply this advanced setting, you first need to activate the you need to activate the manual mode, and you can do it by just doing the save event cards dot set manual mode. After putting this command, you can directly access every variable that is related to your event and event selection. You can just call it and put the cart according to your analysis. You can also change the resolution of SPD vertex. You can also change the distance between the track vertex and SPD. All those things you can do here. You can also put some additional pile-up cart. So as I mentioned earlier, that the pile-up in the pile-up cat, we generally, by default, we use the correlation between the V0 and CL0 or CL1. You can also do the correlation between different detector like TPC and ITS and all those things in order to reject more events. More pileup event that is coming from the TPC pileup. So these things is completely dependent on your analysis, which analysis you are doing and how your analysis is sensitive to those pileup and which pileup you need to do. So for example, here I show just how you can uh, use the pileup rejection card using the correlation between the ITS and TPC. You can directly call the set reject TPC pileup with ITS and TPC cluster correlation. If you put it K true, it will using the correlation between the TPC and ITS cluster and reject the event from your analyzed from your accepted events. So in this way, these are very means this card is basically reject a huge amount of events. For example, it reject if you put a default card, it's remove around 32% of the event. Now you can also control this card by losing this pile up event cards, this pile up selection card of this TPC and ITS correlation by putting argument 2, 3, and 4. And you can see as I increase the order of the argument, the pile up, the event rejection due to this pile up thing is gradually reduced. In the second, if you put 2, it will basically reduce 80% of the event. If you put 3, it will basically reduce 11% of the total event. If you put 4, it will basically reduce the 6% of the total event. In this way, you can also do a systematic study on your observable due to this pileup, due to this TPC pileup. Now, so these are basically the all using which you can implement this event selection, using the event selection over the vertex Z and some basic physics selection cart and the pileup rejection cart. Now I will go to the last topic, which is basically the centrality estimation. So how can we do the centrality estimation? We can do the centrality estimation by just calling a class that is known as AliMal selection. So what you need to do, you need to define the object of AliMal selection by using this command, where this event is basically your event type. If it is a ESD event, then it's basically your pointer of the ESD event. If it is a AOD event, then it is pointer of the AOD event. Then you can directly get the multiplicity percentile from this object by calling the get multiplicity percentile. And in the argument, you need to put the uh, condition of uh, the means the detector using which you want to estimate the multiplicity, using which you want to estimate the centrality. If you want to get the centrality percentile using the V0M, you can put it V0M. If you want to do it using the TPC, you can put it TPC directly here. In this way, it will just return you a float number, which is basically the centrality percentile of your event. In this way, you can directly select the centrality percentile for your event. So that's it for today. And tomorrow I will go to the how we can implement the track selection card and how can we select some track using some PID information from the TPC and TOF and all those things. And in the last day or in the hand on experience session, we will basically see how we implement these cards in our analysis task skeleton that I showed you yesterday. And we will do some proper analysis using those proper event selection and track selection part on the last day of this lecture. So that's it from my side. Thanks. If you have any question, you can ask. Hello, can you hear me?
Yes, sir. have to speak a bit slow because Sourav is taking a lesson with my office. The point here, I think that Mia has pointed that it would be, let's say, also good not to use the other measurements, even if I think that Andrea is right that we can use it, because once we correct for it, we as let's say we believe it as a measurement from the measures, but there are other methods that maybe they were those that Mia was thinking of.
Hello?
For example, the one
Hello?
that
Yeah.
by the CMS
Is there an,
computed
I hear some, is it from your side, Sourav? Looks
Sorry?
like, yeah, I hear some sound from background.
Yeah, so my lab made mean my
Okay,
office.
no, fine, it's okay. So is there any question? Any additional question to Sourav? No, so looks like everybody is tired. Okay, if not, then we conclude today's session. Thanks, Sourav.